I'm Professor Red, and this is Precalc video 321, composing trig functions of the form inverse trig of trig. So in our last video, we looked at the opposite. We looked at taking a trig function and inserting an inverse trig function into it. So in this video, we're going to be going in the reverse direction. We're going to take the inverse trig of a trig function. So remember, inverse trig is going to spit out an angle, so we should expect our answer to be likely something involving pi for radians. So long as the angle is in the restricted domain. So if the angle is not in the restricted domain, that's where we're going to be using some of the skills that we worked to develop. I think it was in 318 when we were trying to figure out theta, right? Determining a value for theta. So that's where this is going to come into play, going to be helpful. So just a reminder for our restricted domains, the restricted domain for sine, tangent, and cosecant is in the east. And when we say in the east, we mean specifically from negative pi halves to positive pi halves. And then for cosine, cotangent, and secant, that restricted domain is in the north, meaning from 0 to pi. So let's take a look at these first three examples and see if they live where we need them to live. So for inverse sine of 2 pi fifths, 2 pi over 5, let's see, if I'm thinking in terms of pi fifths, here's 5 pi over 5, and then half of that is 2.5. So 2 pi over 5 is going to live over here in the first quadrant, which is okay. The first quadrant is good actually for both. So we're going to get 2 pi fifths as our answer. For this next one, we have inverse cosine of 5 pi over 7. So let's envision where 5 pi over 7 lives. So I'm breaking up my axis in terms of pi sevenths. So this would be 7 pi over 7. And just because my pictures are so small, I'm just writing the numerator because that's the important part, right? So here's 7 pi over 7. Half of 7 is 3.5. So 5 pi over 7 is going to land us somewhere over here. So we're in the second quadrant. Cosine lands us in the north. So that's totally fine. So we're going to end up getting 5 pi over 7. They undo perfectly. All right, so let's take a look at part C. For part C, we have inverse tangent of negative 2 pi over 9. So let's envision where that lives. So we've got negative, so I'm going to be going in this direction. And here's my negative 9 pi over 9, since that's my denominator. Half of 9 is 4.5. So here we have negative 4.5. So negative 2 is certainly before negative 4.5. So we're living over here. Tangent lands us in the east. So because this is negative 2 pi over 9, it's between negative pi halves and positive pi halves. So it works. We get negative 2 pi over 9. All right, so far so good. All of our examples are working the way we want them to. Let's just carry on. So for part D, we have inverse sine of 5 pi over 9. I feel like I'm going to run out of room, so let me draw this one over here. So we have 5 pi over 9. So that means this is our 9 pi over 9. And half of 9 is 4.5. So 5 pi over 9 is going to land us someplace like right here. So between 4.5 and 9. Now we hit a little bit of a speed bump because sine has to be in the east. And this angle is landing in the west. So now we have to do some work. So here's how we do the work to figure it out. So we need to reflect this angle over into the first quadrant so that it'll have the same sign. It'll have the same y value. So this angle that we drew is 5 pi over 9, which means that it's 4 away from 9, right? 5 pi over 9 subtracted from 9 pi over 9 is 4 pi over 9. So that means that this distance here is 4 pi over 9. So since we're symmetric when we reflect it, means that distance is also 4 pi over 9. So inverse sine of 5 pi over 9 is 4 pi over 9. So this is an instance where the inverse trig function is not undoing the trig function perfectly. We're getting a different angle because of this restricted domain. So let's go ahead and try the next two, which are also going to have a similar result. We're going to have to reflect it to a matching angle. So here we have inverse cosine of negative 14 pi over 5. Oof, okay. So let's see here. If I'm going in the negative direction, this is negative 5 pi over 5. Then negative 10 pi over 5. And then finally, negative 15 pi over 5. So what we're really doing is we're going around the circle once and then half again to get to this negative 15 pi over 5. When I think about the y-axis label, half of 5 is 2.5. So this is going to be a negative 2.5 pi over 5. 5 plus 2.5 is 7.5. So this is negative 7.5 pi over 5. Here's 10. So 10 plus 2.5 is going to give me negative 12.5 pi over 5. Whew. Okay, so a lot of work in figuring out where we land for this one. We've got negative 14 pi over 5. So we're going to be between negative 12.5 and negative 15. So we're landing over here with our negative 14 pi over 5. Now, whether we live in the east or the north, we never know what's going on in this bottom left-hand quadrant here. So we're going to have to reflect that either into the east or into the north. Because this is cosine, we're going to reflect it into the north. So cosine goes into the north. If it had been sine, we would have reflected it into the east because sine is in the east. So be careful. You want to make sure you know which one you're working with and where it ought to be reflected to. So now, because I'm cosine, right? We're doing cosine. That's the x value. We want that to be the same. So we're going to reflect into the north. And now we have to figure out what's the measurement of this angle. So there are a few different ways you can do this. You can go ahead and do what we did here, use some symmetry. But the way that we did this back in video 318 was we kind of wrote out the fifths. So I'm going to do that just so we can see, the difference and compare which one we like better. So if we were writing out the fifths here, we would get something like this. So this would be negative 1/5, 2/5, 3/5, 4/5, 5/5. Not drawing these perfectly symmetric, just giving me something to count. So this would be 1/5, 2/5, 3/5, 4/5, 5/5. Definitely not properly spaced, but it gets me something to count, gives me the right idea. So because I have to be between 0 and pi, I don't want to continue counting in this direction. I want to figure out what is this angle counting from the right. So if I count from the right, that's going to be 1/5, 2/5, 3/5, 4/5. So this is going to equal 4 pi over 5. If I wanted to use symmetry to figure this one out, I can do that as well. So this was negative 14 pi over 5. That's what we had. So it's 1 pi away, 1 pi-5th away from the axis. So that means this has to be 1 pi-5th away from the axis. So that means this has to be 4 pi-5ths. So you can use your symmetry and your additions to kind of get things through. So this is 1/5 away or 1 pi-5th away. So this has to be 1 pi-5th away. And so that means this would have had to cover 4 pi-5ths. So that's where we're getting 4 pi-5ths using the symmetry instead of those dotted lines to count. All right, so let's do this last one together. I'm going to clear some space for me to be able to do that one. So we have inverse tangent of 9 pi over 8. So since we have tangent, tangent lands us in the east. So I'm going to be interested in landing this angle somewhere in the east. Because the denominator is 8, I'm going to split this up into 8s, and we're positive, so we're going to go counterclockwise. So here's 0 pi over 8, 8 pi over 8, and half of 8 is 4. And so this will be 12 pi over 8. And I can stop because I found the boundaries between where 9 pi over 8 is going to live. So 9 pi over 8 is going to live between 8 pi over 8 and 12 pi over 8. So that's how I know when I can stop going around and labeling the axes. So let's sketch out 9 pi over 8. So 9 pi over 8 is going to be just after 8 pi over 8. And I need to reflect that somewhere into the east so that it has the same tangent value. Now, tangent and cotangent are always tricky because they rely on both x and y. So over here in the third quadrant, tangent is negative or positive. So I need to reflect this someplace up here to make it positive. So let's take a moment and work through reflecting first over into quadrant 2. And then we'll reflect it up into quadrant 1 so we have the right proportions and everything. So first I'm going to reflect it over here. Do a little dotted line here. Now 9 pi over 8 is 1 pi over 8 away from the axis. So I'm thinking that this is a negative pi over 8. And then I need to reflect that up into the first quadrant here. So because this is negative pi over 8, this is going to be a positive pi over 8. So this is going to give us pi over 8. Again, if the reflection movement isn't your jam, you can redraw this using those divisors. So I'm going to redraw this picture so we can see what it would look like if we use that other technique. So I've still got my 8 pi over 8. 4 pi over 8, 12 pi over 8, and 0. And then I want to divide this up into eighths in the top and eighths in the bottom. So let's divide them up like that first. And then we can divide each of those wedges in half. So now if we counted 9 pi over 8, if this one's 8, here's 9 pi over 8. So if we reflected this line through the origin, we're going to get our single pi over 8. So this would be another way to envision or think about this problem. Whew. All right, so we've done a few where we have the same trig function, but as before, we don't need to have the same trig function. So for instance, we could have inverse sine of cosine. So let's see what that's going to look like. For this example, we're going to do two problems. We're going to figure out inverse sine of cosine of 2 pi fifths, and we're going to figure out inverse cosine of sine of pi sevenths. Now, in order to figure out these values, we're going to use a property that we actually discovered when we were working on graphing trig functions. So in our very first graphing sine and cosine function videos, we had cosine of theta was equal to sine of theta plus pi halves. And we were able to derive that identity by taking the sine curve and shifting it to the left by pi halves, and we would get cosine. And then similarly, if we take the cosine curve and we shift it to the right by pi halves, we get the sine curve. So we're going to be using these two equations as we work through these identities or problems. So the reason we're going to do that is because in order to figure out inverse sine of something, we really need it to be in terms of sine. So we want them to be in terms of the same trig function. So my first step here is to rewrite cosine of 2 pi fifths as sine of something. So I'm going to use this first equation here where cosine of theta is sine of theta plus pi halves. So in this example, 2 pi fifths is playing the role of theta. So we're going to have sine of 2 pi fifths plus pi halves. In other words, this is going to be, let's see, that's going to be 4 plus 5 is 9 pi over 10. So that's our first step, is to rewrite this different trig function using the shifting identities here to rewrite it. Secondly, we can go ahead and rewrite it, and then we can solve it like we just did with the previous examples. So we have inverse sine. Now we have sine of 9 pi over 10. So let's sketch out where 9 pi over 10 lives. So if this is my 10 pi over 10, 9 pi over 10 is going to be pretty close to that. Now, if this was cosine, we'd be in a good shape because we're in the north, but it's not. We need to reflect it so we're in the east. So sine is the y value, so we're going to reflect it over here. 9 pi over 10 is 1 away from the axis. So that means that this is going to be a pi over 10. So we end up getting pi over 10. All right, so that's it for that first example. I'm going to jump out of the way for a moment. Well, not really jump, more kind of wander. If you want to, you can pause the video here and try example B on your own. It's going to be real similar to example A, except instead of using the cosine equation, we're going to use the sine equation so we can get everything into terms of cosine. So pause the video here and work through it. And when you're all done, you can unpause and we'll have the answer on the board to review together. All right, so let's see how we did. So first I rewrote sine of pi sevenths in terms of cosine. So I did that by subtracting pi halves from pi sevenths. So I rewrote it with my common denominator this time. So I had multiplied this one by 2 over 2 to get 2 pi over 14. And then this one I multiplied by 7 over 7 to get 7 pi over 14. When I subtracted, 2 minus 7 gave me a negative 5. So I have a negative 5 pi over 14. So for my second step, I have inverse cosine of negative 5 pi over 14. So negative 5 pi over 14 landed me here in the fourth quadrant, but cosine needs to be an angle in the north. So I was able to reflect that to the top and I got 5 pi over 14. So how did you do? Were you able to figure that one out as well? So I find that this reflecting thing helped me personally a lot when I was trying to undo trig expressions. So I'm hoping that this is helping you as well. That's going to conclude today's video, this video on this topic. In our next video, we're going to develop a new property that's going to allow us to use inverse sine, inverse cosine, and inverse tangent keys on our calculator to come up with inverse cosine, inverse secant, and inverse cotangent, as well as just how to use our calculators to find those values anyway. So I hope you found this video helpful, and I hope you have a most fantastic day, and I'll see you next time. Bye for now.